Thermal shock cracking damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of thermal shock cracking based on API 571. A form of thermal fatigue cracking, thermal shock, can occur when high and non-uniform thermal stresses develop over a relatively short time in a piece of equipment due to differential expansion or contraction. If the thermal expansion/contraction is restrained, stresses above the yield strength of the material can result. Thermal shock usually occurs when a colder liquid contacts a warmer metal surface. Thermal shock cracking is a type of mechanical failure that occurs in materials, particularly brittle materials like ceramics, glass, and some metals, due to rapid changes in temperature. When a material experiences a sudden temperature differential, it can undergo expansion or contraction at uneven rates across its structure. This discrepancy can induce significant internal stresses that surpass the material's tensile strength, leading to the formation of cracks. Description of thermal shock cracking damage. Number 1 is from cause of thermal shock point of view. Thermal shock arises when there is a sudden or significant temperature differential across a material. For instance, if one side of an object is heated while the other side remains cool, the differential expansion can create internal stresses. Number 2 is from crack formation of thermal shock point of view. The damage manifests as visible cracks that can vary in size and orientation. These cracks often initiate at the surface of the material and can propagate inward, creating a network of fractures. Number 3 is from patterns and characteristics of thermal shock point of view. The cracks may exhibit distinct patterns, such as spiderweb-like formations or linear splits. The characteristics depend on the material type, temperature change magnitude, and structural geometry. Number 4 is from location and concentration of thermal shock point of view. Areas subjected to the greatest thermal gradients, such as edges, corners, or surfaces exposed to direct heat sources, are most susceptible to crack initiation. The concentration of thermal stress in these regions is where damage is most likely to occur. Number 5 is from material integrity of thermal shock point of view. Thermal shock cracking compromises the structural integrity of the affected material. It can lead to loss of functionality, reduced load-bearing capacity, and failure in applications where reliability is crucial. Number 6 is from post-failure behavior of thermal shock point of view. In some cases, thermal shock damage may not result in immediate catastrophic failure, but the presence of cracks can weaken the material over time, leading to progressive deterioration or complete failure under normal operational conditions. Number 7 is from prevention and mitigation of thermal shock point of view. Understanding the thermal properties of materials and avoiding rapid temperature changes are key to preventing thermal shock. Engineering solutions such as gradual heating or cooling, material choice selection, and design modifications can help mitigate the risk. In summary, thermal shock cracking is a critical concern in various industries, including aerospace, automotive, and manufacturing, where materials are exposed to drastic temperature fluctuations. Effective management of thermal stresses is essential for ensuring longevity and reliability in such systems. Thermal shock cracking affected materials based on API 571, all metals and alloys. Thermal shock cracking is a damage mechanism that occurs when a material experiences rapid temperature changes, leading to differential expansion or contraction within the material. This can cause stresses that exceed the material's strength, resulting in cracks. The materials that are most commonly affected by thermal shock cracking include: Number 1 is ceramics. Many ceramic materials are particularly susceptible to thermal shock due to their low thermal conductivity and brittleness. Examples include porcelain, brick, and various engineering ceramics used in high-temperature applications. Number 2 is glass. Similar to ceramics, glass is also prone to thermal shock cracking because of its brittleness and the large temperature gradients that can occur. Number 3 is metals. While metals generally have higher ductility and toughness, they can still suffer from thermal shock if subjected to rapid temperature changes, especially in cases where there are residual stresses or pre-existing flaws. Number 4 is concrete. In high-temperature applications, such as in furnace linings or during rapid cooling processes, concrete can also experience thermal shock cracking. This can lead to spalling and reduce structural integrity. Number 5 is composites. Some composite materials can be affected by thermal shock if the matrix and reinforcement have significantly different thermal expansion properties. Number 6 is rocks and geological materials. In geological contexts, thermal shock can affect rocks, particularly those that undergo rapid changes in temperature due to volcanic activity or other natural processes. These materials can suffer from thermal shock cracking when subjected to a sudden change in temperature, such as: the first is being exposed to a flame or high-temperature source. The second is being rapidly cooled or heated. The third is being subjected to thermal cycling, or repeated heating and cooling. In general, materials that are brittle, have low thermal conductivity, or exhibit significant differences in thermal expansion coefficients are more susceptible to thermal shock cracking. The design and usage conditions of these materials often need to account for potential thermal shock to mitigate damage. Critical factors of thermal shock cracking based on API 571. The magnitude of the temperature differential and the coefficient of thermal expansion of the material determine the magnitude of the stress. Cyclic stresses generated by temperature cycling of the material may initiate fatigue cracks. Stainless steels have higher coefficients of thermal expansion than carbon and alloy steels or nickel-base alloys and are more likely to see higher stresses. High temperature exposure during a fire. Temperature changes that can result from water quenching as a result of rain deluges. Fracture is related to constraint on a component that prevents the component from expanding or contracting with a change in temperature. Cracking in cast components such as valves may initiate at casting flaws on the ID and progress through the thickness. Thick sections can develop high thermal gradients. Thermal shock cracking occurs when a material experiences a sudden change in temperature, leading to stress concentrations that can exceed the material's strength limits. Several critical factors influence this damage mechanism. Number 1 is material properties, include, the first is thermal conductivity. Poor thermal conductors can lead to large temperature gradients, increasing the likelihood of thermal shock. The second is elastic modulus. Higher elastic moduli can result in greater stress development during rapid temperature changes. The third is coefficient of thermal expansion, or CTE. Materials with high CTE are more susceptible to thermal stress due to expansion and contraction. The fourth is fracture toughness. A material's ability to resist crack propagation plays a significant role in mitigating thermal shock damage. Number 2 is temperature gradient, include, the first is rate of heating and cooling. Rapid temperature changes create high thermal gradients, leading to increased stress and a greater likelihood of cracking. The second is magnitude of temperature change. The larger the temperature change, the more significant the stresses that develop due to thermal expansion or contraction. Number 3 is geometric factors, include, the first is thickness. Thicker sections of material tend to exhibit larger temperature gradients and stress concentrations. The second is shape and size. Irregular geometries can create stress concentrators, leading to localized thermal shock susceptibility. Number 4 is pre-existing flaws. Microstructural defects, such as voids, inclusions, or microcracks, can significantly reduce a material's resistance to thermal shock by providing starting points for crack propagation. Number 5 is initial microstructure, include, the first is grain size. Smaller grains can impede crack propagation and may enhance resistance to thermal shock. The second is phase distribution. In multiphase materials, the distribution and bonding of different phases can significantly affect thermal shock resistance. Number 6 is environment, include, the first is presence of fluids. For example, rapid cooling by water can enhance thermal shock conditions due to the high heat transfer rates involved. The second is oxidation or corrosion. these processes can alter the mechanical properties of materials over time, making them more vulnerable to thermal shock. The third is ambient conditions. The surrounding temperature and medium, such as air, water, can influence how quickly a material gains or loses heat. Number 7 is loading conditions. External stresses applied to the material prior to thermal shock can exacerbate cracking. This includes preloading or residual stresses from manufacturing processes. Number 8 is time of exposure. The duration for which the material is exposed to the thermal shock can also be a factor. Even short, intense exposure can lead to failure if conditions are right. Number 9 is thermal history. The prior temperature exposures and thermal cycling history can affect the mechanical properties and fatigue behavior of the material. Understanding these critical factors is essential for material selection and engineering applications where thermal shock is a potential failure mode, such as in ceramics, glass, metals, and composite materials. Proper design, material choice, and process control can help mitigate the risks associated with thermal shock cracking. Thermal shock cracking affected units or equipment based on API 571, the first is FCC. Cokers, catalytic reforming and high-severity hydroprocessing units are high-temperature units where thermal shock is possible. The second is high-temperature piping and equipment in any unit can be affected. The third is materials that have lost ductility, such as CRMO equipment, temper embrittlement, are particularly susceptible to thermal shock. The fourth is equipment subjected to accelerated cooling procedures to minimize shutdown time. Thermal shock cracking is a damage mechanism that can affect various types of units and equipment, particularly those that experience rapid temperature changes. Some of the commonly affected units or equipment include: Number 1 is furnaces and boilers. The intense heat and rapid cooling cycles can lead to thermal shock in refractory linings and other structural components. Number 2 is heat exchangers. Rapid temperature fluctuations can cause thermal stresses, leading to cracking in tubes or shell structures. Number 3 is pressure vessels. These can experience thermal shock from rapid heating or cooling, especially in processes where temperature changes are abrupt. Number 4 is pipelines. Sudden changes in temperature can induce thermal stress and cracking in piping materials, particularly in those transporting hot fluids. Number 5 is turbines. Areas exposed to high temperatures followed by rapid cooling, such as turbine blades, can suffer from thermal shock-related fatigue and cracking. Number 6 is casting and molding equipment. In processes involving molten metals or plastics, rapid cooling can result in cracking of molds or the cast products. Number 7 is kilns. In ceramic or glass manufacturing, rapid heating and cooling can cause thermal shock cracking in the kiln structure and the items being processed. Number 8 is concrete structures. Large concrete structures subjected to rapid temperature changes can experience cracking due to thermal expansion and contraction. Number 9 is industrial ovens. Ovens used in curing, drying, or other thermal processes can cause thermal shock in materials that are temperature sensitive. Number 10 is nuclear reactors. Components within reactors, particularly in the core and cooling systems, can be severely affected by thermal shock due to rapid changes in operating conditions. Number 11 is electronics and electrical equipment. Components exposed to significant temperature variations may experience cracking or failure due to thermal shock. Preventive measures can include proper material selection, gradual temperature changes, and careful design to accommodate expected thermal stresses. Appearance or morphology of thermal shock cracking based on API 571, surface-initiating cracks may also appear as craze cracks. Thermal shock cracking is a damage mechanism that occurs in materials due to rapid temperature changes, leading to differential expansion or contraction within the material. The morphology or appearance of thermal shock cracking can vary depending on the material and the conditions under which the thermal shock occurs. There are some common characteristics of the morphology or appearance of thermal shock cracking. Number 1 is crack formation. The most prominent feature of thermal shock damage is the presence of cracks. These cracks can appear suddenly and may propagate rapidly due to the stress induced by temperature gradients. Number 2 is orientation. Cracks often have a characteristic orientation that reflects the direction of thermal stress. They can be straight, jagged, or branching, depending on the material's properties and the nature of the thermal shock. Number 3 is surface features. On the surface of the material, thermal shock cracks may appear as visible separations or disruptions. They can be fine or coarse, and the surface may show signs of spalling or chipping. Number 4 is fracture surface characteristics. The surfaces of the fractures may display signs of brittle fracture, with a glassy or shiny appearance, indicating sudden failure rather than progressive damage. Number 5 is chipping or spalling. In certain cases, especially in ceramics, thermal shock can lead to chipping or spalling of material at the edges of the cracks, resulting in small fragments being dislodged from the surface. Number 6 is depth. Cracks can penetrate varying depths into the material. In some cases, they may be shallow and confined to the surface, while in others, they can extend deep into the bulk material. Number 7 is patterning. In certain materials, cracks may form complex patterns resembling a spider web or other geometric configurations. This is typically a result of the material's microstructure and how it responds to stress. Number 8 is discoloration. Thermal shock may also lead to discoloration or changes in surface texture around the crack areas, indicative of thermal degradation or chemical changes in the material. Number 9 is fragmentation. In more severe cases, especially with brittle materials like ceramics or glass, thermal shock can lead to fragmentation, resulting in multiple pieces of broken material. Number 10 is residual stress patterns. The material may exhibit residual stress patterns due to the uneven distribution of temperature and stresses within the material, which might be observable through methods like X-ray diffraction or thermal imaging. Overall, the appearance of thermal shock cracking is critical in assessing the integrity of materials exposed to rapid temperature changes, and understanding these morphological features is essential for material selection and failure analysis. Thermal shock cracking prevention and mitigation based on API 571. The first is prevent interruptions in the flow of high-temperature lines. The second is designed to minimize severe restraint. The third is install thermal sleeves to prevent liquid impingement on the pressure boundary components. The fourth is minimize rain or fire water deluge situations. The fifth is review hot/cold injection points for potential thermal shock. Prevention and mitigation of thermal shock cracking damage can be achieved through a combination of design, material selection, and operational strategies. Number 1 is design considerations. Include, the first is gradual temperature changes, design systems to allow for gradual temperature changes, reducing the thermal gradient and stress on materials. The second is thermal expansion accommodation, provide sufficient clearance and flexibility in the design to accommodate thermal expansion and contraction. The third is stress analysis, conduct stress analysis to identify potential thermal shock cracking areas and design modifications to mitigate them. The fourth is material selection, choose materials with suitable thermal expansion coefficients, thermal conductivity, and mechanical properties to minimize thermal shock cracking risk. Number 2 is material selection. Include, the first is low thermal expansion materials, select materials with low thermal expansion coefficients, such as ceramics, glass, or certain polymers, to reduce thermal stress. The second is high thermal conductivity materials, use materials with high thermal conductivity, like copper or aluminum, to facilitate heat transfer and reduce thermal gradients. The third is ductile materials, choose ductile materials, like certain metals or polymers, that can absorb thermal stresses without cracking. Number 3 is operational strategies. Include, the first is gradual startup and shutdown, implement gradual startup and shutdown procedures to minimize thermal shocks. The second is temperature control, maintain uniform temperatures and avoid sudden temperature changes. The third is cooling and heating rates, control cooling and heating rates to prevent excessive thermal stresses. The fourth is regular maintenance, perform regular maintenance and inspection to detect potential issues before they lead to thermal shock cracking. Number 4 is additional measures, include, the first is thermal insulation, apply thermal insulation to minimize heat transfer and reduce thermal gradients. The second is stress relief, implement stress relief techniques, such as heat treatment or peening, to reduce residual stresses. The third is surface treatment, apply surface treatments, like coatings or linings, to reduce thermal shock cracking risk. The fourth is monitoring and inspection, regularly monitor and inspect equipment for signs of thermal shock cracking, such as cracks, deformations, or unusual noise. By implementing these prevention and mitigation measures, you can reduce the risk of thermal shock cracking damage and ensure the safe and reliable operation of your equipment. Thermal shock damage inspection and monitoring method based on API 571. The first is this type of damage is highly localized and difficult to locate. The second is PT and MT can be used to confirm cracking. Thermal shock cracking can occur in materials subjected to rapid temperature changes, leading to cracks and structural integrity issues. Inspecting and monitoring for thermal shock cracking damage typically involves a combination of visual inspections, non-destructive testing, NDT, methods, and monitoring techniques. Here are some commonly used inspection and monitoring methods. Number 1 is visual inspection, include, the first is surface examination, inspecting the surface for visible cracks, discoloration, or other signs of distress. The second is compare with baseline, checking against historical images or data to identify new or enlarging cracks. Number 2 is non-destructive testing, or NDT, include, the first is ultrasonic testing, or UT, uses high-frequency sound waves to detect internal flaws or cracks. Variations in sound transmission can indicate damage. The second is radiographic testing, or RT, X-ray or gamma-ray imaging can reveal internal cracks or anomalies, but it is less common for surface-level issues. The third is magnetic particle testing, or MPT, effective for detecting surface cracks in ferromagnetic materials, issues. The fourth is dye penetrant testing, or DPT, a liquid penetrant is applied to the surface, which can reveal cracks when a developer is applied after the penetrate is removed. The fifth is eddy current testing, or ECT, utilizes electromagnetic fields to detect surface and near-surface cracks, particularly in conductive materials. Number 3 is thermal imaging, include, the first is infrared thermography, detects temperature variations on the surface, which can indicate the presence of cracks or defects due to differing heat flow. Number 4 is acoustic emission monitoring, this method detects high-frequency sound waves produced by crack propagation. It requires ongoing monitoring and data analysis to interpret results accurately. Number 5 is vibration analysis, used in rotating equipment or structures where thermal shock might cause cracks. Changes in vibration patterns may indicate damage. Number 6 is strain gauges, these can be installed to measure stress and strain within materials to monitor the structural response under thermal conditions continuously. Number 7 is moisture content measurements, in some applications, monitoring for moisture within materials can signify areas susceptible to thermal shock, especially in concrete or ceramics. Number 8 is time-lapse photography or video monitoring, capturing changes over time can provide evidence of crack development and progression. Number 9 is computer modeling and simulation, advanced software models can simulate thermal impacts and predict where thermal shock cracking is likely to occur, allowing for proactive inspections. In conclusion, selecting the right method for monitoring and inspecting thermal shock cracking depends on the type of material, the environment, and the specific application. A combination of these methods is often used for a comprehensive assessment to ensure structural integrity and safety. Thank you.